All right, welcome back, scholars, to lesson 2, where we're going to spend some time talking about how to graph functions. As you can see, we have an extensive bit of vocabulary for today's content, so make sure you Google those definitions. Today, we're going to be learning to describe whether or not a mathematical expression is a relation or a function, so I can identify the domain and graphical behavior of a function. I'll know I've got it when I can use the characteristics of functions to represent them on graphs. I'm going to beat a dead horse here, for lack of a better expression. But what separates, the general population that understand mathematics to those of you that are going to find yourselves in advanced mathematics courses and successful in those mathematical courses is this ability to conceptually understand what is happening graphically and connecting it to the algebra that you've become so comfortable working with. This is one of those foundational lessons. Right, so the most important way to visualize a function is through its graph. To graph a function f, we plot the points x. I'm going to use a lot of notation today to kind of throw you off your game and force you to elevate. Right, so we plot the points x, f of x in a coordinate plane. The graph of f is the set of all points x, y, whose such that y equals f of x. The graph of a function f gives us a picture of the behavior or the life history of the function. Functions of the same type display similar tendencies or behaviors, so it is critical that we're able to identify the structure of those functions. In the next unit, we'll be more able to discern the various features and characteristics like and behavior, roots, intercepts, multiplicity, etc., associated with even and odd degreed functions. For now, we're going to take a slow, methodical walk through all of this content. So I have some function structures over here on the right-hand side. We can, or mathematicians have labeled these functions because they all represent similar behavior. So if we have some type of function that's equal to a numerical value, we would call that a constant function. That's awkward. I'll make sure that is text for when you're doing your own notes. We have f of x equals mx plus b, which many of you should remember that is your linear function. F of x equals x to some power of n being greater than, that should not be 0, that should be 1. That would make it a power function. This is why you should always edit before submitting your assignments. And then this last expression here, f of x equals x to the 1 divided by n, we would call that a root function. Okay, those are all part of your definitions for this today's video, so you should be able to connect the dots. In the event you cannot recall the behavior of a function, to create a graphical representation, never forget a table of values should be created. Right, that is your first go-to in case you cannot remember. So in the event here, right, we have this function x squared minus 4 that we're going to graph accordingly. At the input of -3, we would get -3 to the second power. So minus 4, it's going to be a 9 minus 4, which is going to be 5. And if you replicate that process on the opposite side, because we have a quadratic function, we know that this is a symmetrical type of function. 2 squared is 4, so that would give me 0. This would be -3, -4, -3, oops, and 0. And remember, this table of values is creating for us a set of points, right? So at -3, the output is 5. So -3, +5, -2, 0, -1, -3, a y-intercept of -4. Right, and what's more important here is this idea of, yes, it's important to get the points, but we're more concerned with more concerned with the actual features, right? Like the intercepts. Okay. We'll talk a little bit next unit about, why does this graph go straight through the x-axis? Why isn't it bouncing? Things of that nature, but things you wouldn't have to necessarily concern yourself with. So over the next 2 slides, you'll be tasked with graphing, I think it's 3 slides actually, yeah, 3 slides. You're going to be tasked with graphing a few different functions just using a table of values. Eventually we'll get to the point when you'll be able to look at something like this and be able to create a rough sketch based on some identifiers, but make your way through these methodically. um, I've forced you to use these points on your enhancement opportunities. You'll have the opportunity to select your own points. But let's get into the main point of today's content, which would be continuity. All right, so last lesson, we spoke at great length about a function, its origins, what makes a function, but we would say that a function is continuous if it has no breaks or no poles. So if you were to sketch a function, this means that you can put your pencil on the left-hand side, sketch, make your way all the way to the right side without lifting up the point. If you have to lift up the point and then put it back down to indicate there's a new starting point, that means that the function is not continuous. And we looked at this on Friday, or our past lesson regarding domain. So when there are restrictions on the domain, right, so that means that there are values of x that the function cannot take, we can state that the function is not continuous because the function is therefore broken at those specific points. Now, in terms of what's a function, what's not a function, everything in our world can be defined as a relation, right? That's a set of ordered pairs. In order to elevate from a relation to a function, I'm going to give you a real world example. Think of this idea of a relationship with a significant other. In order for that relationship to function, it is imperative that you maintain a relationship with, or an intimate relationship with, only one person. If you decide to have an intimate relationship with 2 people at the same time, I don't know about you, but it doesn't appear that that relationship will be functioning for too much longer. Okay? So once again, if you have a intimate relationship with another human being, it is imperative that it is with only one other person, because in the event that you have multiple, 2, 3, 4, who knows, maybe 5 different partners or different outputs, if you put all of them in the same room and they found out, I don't think that we could say that your relationship is functioning. Only if you have one intimate partner who you are devoted to and dedicated to can you probably say that your relationship is functioning. So mathematically speaking, what that means is that no 2 ordered pairs may have the same input but different outputs. You are the input. You are the x coordinate, and the output, the y coordinate, is your significant other. So for each input, there can only be one real unique output. Graphically, right? So that's how we're going to determine things algebraically, and we spoke a little bit about that last class and last unit. We have a vertical line test, which says the following. The vertical line test states that a curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. And why does that allow us to say that a graphical representation of a relation is not a function? Well, remember, a vertical line has the same y coordinate at, or not the same, sorry, different y coordinates at the same x coordinate. I don't want to get into the too much nitty gritty here because you're going to be tasked with determining which of these functions, the one on the left or the right, um, does not represent a function. Okay, but just remember, a vertical line has multiple outputs with a single input. Okay, as we said here, for each input, you cannot have multiple outputs. You can only have one output if you want to be defined as a function, right? One significant other, not two, not three, not four, not 50, at least in our American society. After you've done that, you'll be tasked with sorting both equations, coordinates, and graphs into the corresponding relation and function. Okay. Once again, we're still exploring here, so it's understandable if you're unable to reach the 10, but you might be able to determine a pattern, at least visually speaking, maybe not algebraically, but that is okay, and that is what I'm here for and what we'll talk about in class. But any equation in the variables x and y defines a relationship between the variables, right? So we can always say, once again, that you're in a relationship, or any equation that we have is a relationship, right? The word relation is in the word relationship. Does every equation in x and y define y as a function of x? That is the big question, right? You could say that you're dating somebody, but you can't really say that it's going too well if you have 2 or 3 or 4 or 5 different partners, right? Using your thought process in the previous slide, okay, what do you think? Does every equation in x and y define y as a function of x? It's very theoretical, very conceptual. Um, Basically, can we take all of these equations at face value and just say, yeah, they're all functions? Or are they just equations? Or are they just relations? And that brings us to our reference sheet. So these are functions that you're going to use a lot in this class and moving forward. It says, or I put use at your own risk, because I do not recommend downloading these or downloading, memorizing these. It's trivial. If we can focus more on the characteristics and behaviors, you'll be much more successful, because one slight tweak, right? I change this from x squared to 3x squared. You might be like, oh, how do I know what's going to change? Yada yada yada. Right. So use this to reference, but I would not memorize these or download them into your brain. And that's where we'll pause at the enhancement opportunities.